Welcome to today's paper reading. Today's paper is titled, Are Long-LLMs a Necessity for Long Context Tasks? This paper, authored by Hongjin Qian and colleagues from the Zheng School of Artificial Intelligence at Renmin University of China and the Beijing Academy of Artificial Intelligence, is currently under review. The abstract highlights the ongoing challenges in learning and deploying Long-LLMs, despite recent advancements. It argues that Long-LLMs are not necessary for solving long context tasks, as these tasks can be addressed by focusing on short context segments within the long context inputs. To address this, the authors propose the LC-Boost framework, which enables a short LLM to handle long context tasks through a bootstrapping approach. This framework involves the short LLM prompting itself to make two critical decisions: how to access the appropriate context and how to effectively use that context. The LC-Boost framework is evaluated on various long context tasks from popular benchmarks, demonstrating significantly improved performance with reduced resource consumption. Large language models, LLMs, are increasingly used in real-world applications, particularly those involving long sequence inputs like long document question answering and summarization. These applications require LLMs to have a long working context, often referred to as Long-LLMs. However, the learning and deployment of Long-LLMs present significant challenges. Many existing LLMs are initially designed with a limited context size, which can be costly and resource-intensive to expand. This paper argues that long context tasks can be effectively addressed using short context through strategic information extraction, similar to how humans and computers handle long-form problems. To address this, the authors propose LC-Boost, a method that employs short LLMs to solve long context tasks in a bootstrapping manner. LC-Boost operates through two critical reasoning steps: access, where the LLM plans how to access the appropriate context, and utilize, where the LLM determines how to effectively use the accessed context. This design allows LC-Boost to adaptively handle various long context tasks, demonstrating superior performance with lower resource consumption. Figure 1 illustrates the LC-Boost framework, which employs a short LLM to address long context tasks through a bootstrapping approach. The framework involves two key reasoning steps: access, where the LLM determines how to access the appropriate context within the input, and utilize, where the LLM decides how to effectively use the accessed context. This design allows LC-Boost to adaptively handle various long context tasks, such as knowledge-grounded QA problems, by either directly accessing relevant context through retrieval or sequentially scanning the context chunk by chunk for information aggregation. The figure showcases four toy examples: A. Brute force solution, B. Naive RAG, C. LC-Boost with RAG, and D. LC-Boost with divide and conquer, demonstrating the efficiency and effectiveness of LC-Boost in comparison to other methods. The LC-Boost method is designed to handle long context tasks using short context LLMs. It starts with an input query Q and a long context X, aiming to produce an output answer Y. The long context X is decomposed into a series of short contexts, X1, Xn. LC-Boost operates through an iterative decision-making process involving two types of actions: information access and information utilization. The action space A includes actions like task understanding, retrieve, move, append, merge, answer, and aggregation. Each action is predicted by considering the current short context Xi, the input query Q, and all previously extracted relevant information X1, I-1. This allows LC-Boost to dynamically generate the answer Y by accessing and utilizing relevant information in a flexible and efficient manner. Figure 2 illustrates the results of a pilot study conducted across various tasks involving long context problems. In the brute force setting, the entire context is processed by GPT-4-128K, a model capable of handling large contexts. Conversely, in the LC-Boost setting, the context length is restricted to 4K, and LC-Boost is employed to address the long context problem using short contexts. The study reveals that LC-Boost consistently performs as well as or better than the brute force setting, particularly in tasks such as question answering, QA, few-shot learning, and synthetic tasks. This is attributed to the ability of LC-Boost to filter out irrelevant context, thereby enhancing task performance. For tasks like summarization and code completion, which require considering mutual dependencies among short contexts, LC-Boost achieves performance levels equal to or slightly better than the brute force setting, thanks to the optimal compression function provided by GPT-4. In this section, we discussed the experiment settings and main results. We evaluated LC-Boost and baseline models on 12 datasets, including tasks like single.QA and multi.QA. We compared LC-Boost with 3 types of models: short-LLMs with context length less than 32K, long-LLMs with context length of at least 32K, and closed-source LLMs. The main results show that LC-Boost, with a context length of 4K, outperforms all baseline models in most tasks, verifying its capability to handle long context tasks effectively. Long LLMs generally perform better than short LLMs, indicating the effectiveness of fine-tuning for long contexts. However, the performance of long LLMs is not consistently stable across different tasks, suggesting that adapting LLMs to long contexts may compromise their general abilities. Table 1 presents the main experimental results across various tasks, highlighting the performance of LC-Boost and baseline models. Key findings include LC-Boost's superior performance in all tasks except code completion, the general superiority of long LLMs over short LLMs, and E9B200K's exceptional performance in code completion but inconsistent results across other tasks. Table 2 presents case studies from a self-constructed dataset, highlighting the performance of LC-Boost in challenging QA tasks. LC-Boost's dynamic customization of action trajectories allows it to effectively solve problems using shorter context lengths compared to LLMs. The table shows correct answers in teal, incorrect in red, and ambiguous in orange. For instance, in a query about single-author papers at ACL 2023, LC-Boost accurately identifies 8 papers, while other models miss the mark. Another query about petrified people in Harry Potter demonstrates LC-Boost's ability to aggregate information accurately, despite challenges in differentiating between human and non-human entities. Figure 3 compares the performance of various context processing strategies in an ablation study. It highlights that dynamic action trajectories, which customize the action path for each query, significantly enhance performance. This approach is particularly effective in single-doc and multi-doc QA tasks, as it accurately selects the necessary context to answer queries, filtering out irrelevant information. However, in few-shot learning tasks, the dynamic strategies do not show a significant advantage, likely due to the substantial guidance provided by the in-context examples. Figure 4 presents an analysis of energy consumption, comparing the brute force approach with our LC-Boost method. The y-axis is measured in joules. The theoretical energy consumption is estimated for 7 LLMs across varying context lengths. We roughly estimate the energy consumption using the formula total float operation times 400W/312 teraflops, assuming the use of an A100 GPU with a compute capability of 312 teraflops for BFLOAT16 operations and a maximum TDP of 400W. The practical energy consumption is estimated by recording the GPU time and GPU power during inference with different context lengths. We use a Llama 2-7B128K and a Llama 2-7B Chat 4K for the brute force setting and LC-Boost, respectively. Figure 4 clearly indicates that longer context lengths significantly increase energy consumption with the brute force method, especially evident in practical measurements. This difference is primarily due to the need to distribute sequence activation tensors across multiple GPUs in practical experiment, with tensor I/O exacerbating inference latency and thereby inflating energy costs. In contrast, our LC-Boost method, working with 4K context lengths, shows only a mild increase in energy consumption across contexts, thereby confirming its energy efficiency while maintaining comparable or superior performance on long context tasks. We also provide an analysis on token consumption in Appendix C. The research on long context tasks for large language models, LLMs, has primarily focused on 2 main approaches. The first approach involves increasing the working context size of LLMs, significant efforts have been made to extend the context size from 4K to 32K tokens, and more recently, to the million level. However, many current models still operate with context sizes under 32K, such as GPT 3.5 Turbo with a 16K context length. The second approach involves extracting a short surrogate context from the full context, using techniques like retrieval-augmented generation, RAG, and context refinement methods. These methods often use task-specific strategies, such as deploying retrievers to select relevant context chunks. Recent studies have proposed chunking-free methods to maintain semantic coherence. Lastly, reasoning-based methods employ decision-making processes to navigate through long contexts, utilizing techniques like in-context learning and chain-of-thought reasoning. In this paper, the authors argue that long context tasks can be effectively solved using short context methods. They introduce LC-Boost, a method that decomposes long contexts into shorter segments and processes them through a decision-making framework. This approach was validated both theoretically and empirically. The authors conducted experiments on 12 datasets, comparing LC-Boost with long large language models, LLMs, and other baseline models. The empirical results confirm the effectiveness of LC-Boost in handling long context tasks. Additionally, the paper discusses the energy consumption of LC-Boost compared to Long-LLMs, showing that LC-Boost can achieve similar performance with significantly reduced energy usage. The limitations and broader impacts of the research are discussed in Appendix D. Thank you for watching.